So we are on question number 31 of code Q6. Now over here we have given three figures A, B and C, and in the given circuit A, B, C, the potential drop across the two PN junctions are equal in which figure, in which circuit. So over here we can see in the first one, the two are basically acting like a diode and they are basically forward biased, right, over here. So of course current will flow through them and we'll take them as identical ones. So of course potential drop will be equal in the first case. Okay, this is okay. In the second one, you see this first diode is basically forward biased, but over here the other end, you see this one is basically reverse biased. So over here we know that in the forward biased case and the reverse biased case, resistances of a diode are different. So of course potential difference will be unequal over here, right? At the same time, if we talk about the third one, that is C, so this is the reverse case of first one. Again over here the diodes are basically forward biased in this case. We can just say like this, right? At the same time we can say like this. So you see the reverse case of first one. So over here as well, identical, forward biased, both the cases. So here as well the potential will be equal. So we can say that both in circuits A and C will be same. This was the question from the semiconductors PN junction diode, right? So let's just move to the next question. This question is basically from the fluid mechanics, and specifically if we say from the viscous part where we discuss about the viscous forces, and specifically this is about the Stokes law. A spherical ball is dropped in a long column of highly viscous liquid. The curve in the graph shown which represents the speed of the ball as a function of time t is. Now, as we know, whenever we drop a spherical ball in a viscous liquid, right, there will be a drag force based on the Stokes law. So here the velocity initially increases and after some time it will attain a terminal velocity. So the graph of velocity versus time, right, it should be something like this, and we say that it will just attain a terminal velocity over here, right? This will just attain a constant value, so somewhere like this, and we see here option B is correct, right? So from this to, right, let's just move to the next question. 33rd questions, again from the current electricity. Lots of questions are there this year from current electricity. Last year as well, it was the same case. Two resistors of resistance 100 ohm and 200 ohm are connected in a parallel in an electrical circuit. The ratio of the thermal energy developed in 100 ohm to that of 200 ohm in a given time is. Now we know that since both the resistors are connected in parallel, so potential drop across them will be same. So it's better if we just use this formula, that is V square by R into T. Now since both are in parallel, V will be same and given time is given, so T will be also same. So heat generated will be inversely proportional to the resistance. So we will say H1 upon H2 will be equal to R2 by R1. Right. The second resistance is basically over here 200 ohm and first one is 100. So this will be 2 by 1. Right. And correct option over here is option number 2, that is 2:1. Let's just move to the next question part. This question is again from modern physics. We have seen earlier from the Bohr's atomic model as well. Now we are seeing for the modern physics fast and specifically from the topic photoelectric effect. When two monochromatic lights of frequency F, V we will say and V by 2 are incident on a photoelectric metal, their stopping potential becomes Vs by 2 and Vs respectively. The threshold frequency of this metal is. Now this is basically we can just solve this from the Einstein's equation. For the first part we will say H times frequency is equals to E times Vs, kinetic energy maximum, or we can say, and over here this is work function, that is phi, right? And the first case, the Vs is basically half, like Vs by 2. So we will say that this is Vs by 2, right? This is equation number 1. Second equation, for the second time, the frequency is V by 2. So over here I will write, and the stopping potential is Vs, so E times Vs plus phi. Work function won't be changing. So this is equation number 2. Now what we can do over here, we can multiply this equation by 2 and subtract it from equation number 2 only. Why we are doing this? We want to cancel it this Vs, EVS term over here. So if you solve it, you will get 3 by 2 H frequency is equals to phi, and we should know that H times this will be threshold frequency, that is F naught. So H will cancel out, and the threshold frequency, or we can say this V naught, will be 3 by 2V, right? So 3 by 2V, yeah, option number 4th is correct. 3 by 2 times. Now let's just move to the next question. Question number 35, last question of section A. This question is from, again, fluid mechanics part, specifically from the surface tension part. Excess pressure we have to discuss over here. If a soap bubble expands, the pressure inside the bubble is. Now you should know, if there is a soap bubble outside, we can say that the pressure will be P naught, that is atmospheric pressure, and inside there will be some pressure. Let's call it P. So we know that excess pressure for here, the soap bubble will be 4T by R. By 4T. Of course, 2 free surfaces are there for the soap bubble. So over here, if we write P, del P, then it will be P minus P naught is equals to 4T by R. So inside pressure, we have got this P naught plus 4T by R. Now surface tension will not change, P naught will change, and if you expand, if the bubble expands, R will increase and the pressure P part will decrease, since it is an inverse relation. So over here, decreases will be the answer. Pressure will decrease inside the bubble if bubble expands. Next question, as you can see, we are in part section B, where there are 15 questions and we have to attempt only 10. So over here, let's discuss this one by one. 36. This question is basically from the electrostats, specifically from electric dipole. You see, 2 point charges minus Q and Q are placed at a distance L as shown in the figure. The figure is given. The magnitude of the electric field intensity at a distance R, where R is greater L, varies as. Now R is greater L, you see, they are talking about a short dipole. And for the short dipole, if you say, let's say this is a dipole, and we are talking about some point, let's say at an angle theta, we are talking about at point P. This is R. So you should know the general formula that EP is basically Kp by R cube under root 3 cos square theta plus 1. But over here, they are just asking about the dependence of electric field intensity on distance. So over here, 1 upon R cube is there. So second option will be correct. 1 upon R cube. So this is question number 36. Let's just move to the next question. This question 37 is basically from the unit in dimension and specifically from significant figures. The area of the rectangular field in meter square of length 55.5 meter and breadth is 25 meter after rounding off the value for the correct significant digits is. You should know that when we multiply two quantities, right? So the product will be always having the significant figures least among the initial ones, to which we were multiplying. So 55.3 has 3 significant digits and 25 has 2. So of course our product, that is area of rectangle, length into breadth, it should have 2 significant figures. So no need of calculating so much. You see, option number 4 has 2 significant figures. So we can just opt this and move forward, right? No need of just viewing other options. Okay. Now we are on question number 38. This question is from logic gates. The truth table we have to form for the given logic circuit. So over here, one way can be we can just write the formula in the Boolean format, but it's good if we can just eliminate the options from 1, 2, 3 and 4. So it will be good and suitable over here. So you see, first option they are all taking A as 0 and B as 0, right? So let's take A as 0 and B as 0 as well. So when A is 0, it is just entering a NAND gate. So over here 0 and this is again 0. A value 0, B value 0. So I will be getting answer as 1. And over here in this part, this 0 will become 1 before entering into the second NAND gate, and this will be 0. And again this will be 1 only. And when they come off from an AND gate, there will be 1. You see, you can see the options. First one is of course getting cancelled out. Fourth one is also getting cancelled out. Now we are with 2 and 3. Now we have to choose between 2 and 3. So it's better, you see, second one 0, 1 is giving C as 0. Third one 0, 1 is also giving C as 0. So it's better move for the third part. A is 1, B is 0. For that, in option 2, C is given as 0. But in 3, C is given as 1. So let's just check it. Over here, if I say we are just trying to move ahead with the third part now, right? So I will be writing A as 1 and B as 0. So we'll be entering like 1, 0, and the value will be over here 1, right? After coming out from the NAND gate, and over here it will be 0 and this will be 0 as well. So again this will be 1, and C will be getting again 1 for the AND gate. So you see, C is 1 with option 3 and third option is correct, right? So let's move to the next question, that is question number 39 of code Q6. And let me remind you, we are in section B. These are given as like two statements are given. One is they are labeling as assertion and the second one is reason. Now the assertion A is the stretching of a spring is determined by shearing modulus of a material of the spring. You see, when we shear a body, then we can use this term shearing modulus. But over here, like for the spring, we can use the word twisting. But over here, we are actually stretching the spring, right? So we are applying a tensile stress over here. So it will be giving Young's modulus. So again, assertion A is incorrect. Now for reason, a coil spring of copper has more tensile strength than a steel spring of same dimensions. Steel has more tensile strength over here, right? You can just see from the NCERT as well. Spring has more tensile strength. So again, this reason is also incorrect. And now no options are matching over here. So hopefully this question will be cancelled, right? Because both A and R are false, incorrect, and we cannot find any suitable option out of 4. Okay, let's go down to the 40th question. This is from the magnetism and specifically from Ampere's law. From Ampere's circuital law, for a long straight wire of a circuit cross section carrying a steady current, there is a current in the cross section as well. The variation of a magnetic field inside and outside region of the wire is, and we are given with certain options. So over here, let's draw one big cylinder. Of course, this is infinite, right? And there is current inside as well. You see, when we apply Ampere's circuital law, inside B will be directly proportional to R. While when we go outside, it will just behave like a simple infinite wire, and where B will be inversely proportional to R. So we can draw the diagram as well, B with R. So till we are reaching the periphery, or we can say at the boundary, it will be directly proportional relation, and after that it will start decreasing, right? So over here, third option is the best option out of these 4. A linearly increasing function of R up to the boundary, that is correct, directly proportional, I'll say. And after that, and then decreasing one with 1 by r dependence of the outside region. So here it is decreasing like that. So the correct option will be